Inside a conductive wire, you won't see a calm stream. You'll see a violent storm of charged particles surging uncontrollably through the dark. Physicists measure the intensity of this motion as current. We define it mathematically as Q over T, charge divided by time. If exactly 1 coulomb of charge tears past a single imaginary boundary in 1 second, that equals 1 ampere of current. But let those electrons flow with absolutely zero opposition, and you don't get a working machine. You get a catastrophic short circuit, melting wires and destroying components. To actually harness this energy, we have to create friction. We need a physical opposing force to limit that chaotic flow, a property known as resistance. Pushing back against the electrons gives them a surface to work against. Control begins with a calculated obstacle. The physics of that obstacle come down to a simple equation based on physical geometry. Resistance equals the material's resistivity multiplied by its length divided by its cross-sectional area. This line graph tracks what happens when we change the dimensions. As the physical wire stretches longer, the resistance line rises in direct proportion. The current has to fight its way down a longer physical obstacle course, losing energy along the way. But watch this chart shift when we widen the wire's diameter. The resistance drops. Opening up more physical space allows the electrons to pass through with far less opposition. Geometry isn't the only factor at play. A hidden thermodynamic variable constantly alters these values behind the scenes: temperature. When pure metals like copper heat up, their atomic structure vibrates, creating more collisions and driving resistance up. But apply that same heat to insulators or carbon, and the exact opposite happens. The thermal energy frees up trapped electrons, actually dropping the resistance. Resistance is a dynamic property, determined as much by the material's physical architecture as by the heat of its environment. Engineers take these invisible laws of physics and trap them inside standardized manufactured components. If a circuit requires dissipating massive amounts of power, they build wire-wound resistors. By wrapping a tough nickel-chrome alloy tightly around a ceramic core, they create an obstacle capable of handling hundreds of watts without incinerating. For highly delicate, low-power electronics, they use metal film resistors. Here, microscopic layers of metal vapor are baked directly onto a ceramic base, offering highly accurate control over the current. A single resistor is rarely enough to manage a complex machine. Engineers architect entire networks of them, balancing their values to sculpt the perfect electrical pathway.
If you're all about CNC machining, mechanical engineering, and industrial tech, remember to subscribe and share the video around. Much appreciated.